You're welcome to Hexon Academy. Today we're going to discuss screw jack. So this is going to be a complete course on screw jack. And by the end of this video, you should be able to solve confidently all questions relating to screw jack. So let's begin with understanding what screw jack is. Then we go to question. So what is a screw jack? A screw jack is a simple machine, as you can see, that can be used to raise heavy objects like jacking up your car. Again, screw jack can also be used where great compression is needed. So let's look at how screw jack works and the parts of screw jack. The first part in this screw jack we're going to say is the tummy bar. This is referred to as the tummy bar or the arm of the screw jack. Now, this arm is where the effort is applied. So the effort is applied to this arm and it is turned through one revolution. That means this arm here is free to rotate in horizontal circle. That is, it can go horizontal like this through as many revolutions as you want this head to ascend up. All right. So this is where the effort is applied, and this is called the arm of the screw jack. Now, again, another important part is the pitch of the jack. Pitch of the jack, we have all this which we refer to as what? Thread. As thread, I want you to observe this. This thing that spiral around this is called a thread, in case you don't know what thread is. So that is the thread on the body of the jack. So the distance between successive thread is referred to as pitch. So from one thread to the next thread is called pitch. And that is the distance that the head of this jack will move when you turn this through one revolution. So for every one revolution you turn this arm of the tummy bar, this head of this jack will move up through one pitch. So one revolution that this effort creates moves the head of this jack through one pitch. And that implies that this pitch is actually the distance moved by load. And when one revolution is made, then one pitch, the load goes up by one pitch. So you turn this one revolution, then this head moves through one pitch. So distance moved by load will be determined by the pitch, and distance moved by effort will be determined by how many revolutions that this tummy bar is making. Now, I want you to also observe this, that if you turn this through a circle, the effort has gone through one circumference. All right, and as you recall, the circumference of a circle is 2 pi r. So this 2 pi r is the distance moved by effort when the load moves through one pitch. So this gives us distance of what? Effort. This gives us distance of effort when the load moves through one pitch. That is P. So when the load goes up by one pitch, that means the effort has gone round through 2 pi r, because this describes a circle. Let's look at the velocity ratio of screw jack and what it looks like. So let's say VR for velocity ratio, as we know, is the distance moved by effort. The distance moved by effort all over distance moved by load. So velocity ratio is going to be, let's look at distance moved by effort. The effort is going through one revolution. So this effort applied here goes through one circumference. That is 2 pi r. When the effort goes through one circumference, the load goes up by one pitch. So distance moved by load is going to be P. That's one pitch. So for every 2 pi r that you have, then the load goes by one pitch. So this gives us the velocity ratio for screw jack. Take note of this formula. We'll come back to it in a little while. Also note that mechanical advantage is the ratio of load to effort. This gives us mechanical advantage. It's also known as force ratio. So let's also highlight that. Then lastly, efficiency of a machine is mechanical advantage over velocity ratio multiplied by 100%. So these are the three formula we're going to use to solve any problem that comes from here. So let's begin with example 1. In this question, a screw jack has a pitch of 0.5 cm. So we are given pitch. Let's write solution here. We are given pitch as 0.5 cm, all right, and a handle of 25 cm. So the handle of this bar is 25 cm. That is our radius. Okay, so our radius is 25 cm. Okay, from that we were able to determine what 2 pi r will be. If an effort, we are given effort of 150 newton is applied to lift a load of 3000 newton. So we're also given the load as 3000 newton. Okay, calculate the mechanical advantage. That's the first question. Now I want you to recall that mechanical advantage is load over effort from the formula we have established. So what is our load here? Our load is 3000 newton. So we're going to write 3000 newton all over effort. What is our effort? 150 newton. Newton cancel newton. This goes with this. We can check 15 in 15 is 1. 15 in 30 is 2. So this is 20. So the mechanical advantage is 20 and it has no unit. As you can see, Newton has cancelled Newton. All right. So that is for mechanical advantage. Let's go to the next question here, which is the velocity ratio. So the velocity ratio VR is going to be 2 pi r over pitch. Now recall, as I've explained, that 2 pi r is because this effort is going to go through one revolution, that is through one circumference when you turn this tummy bar. So that's why we have distance moved by effort as 2 pi r. And for every one revolution, the load will go up by one pitch. The head of this jack goes up by one pitch. So that gives us the velocity ratio as 2 pi r over what? Pitch. So let's substitute. This is going to be 2 times pi. Let's use 3.142 for pi. Multiply by r. What is the radius given to us? 25 cm upon pitch. Pitch is given to us as 0.5 cm. Now, this is in cm, this is in cm, so cm will cancel out cm. So there's no need to convert this to meters and this to meter. That will be a waste of time. So this is VR, which will be equal to, so our velocity ratio gives us 314.2. Again, there's no unit because this cm will cancel out the cm you have here. So we have gotten the mechanical advantage. We have also gotten the velocity ratio. So the next is to calculate the efficiency of this system. So I'm going to clean the board and we work the efficiency of the system. Efficiency is mechanical advantage over velocity ratio multiplied by 100%. Now this gives us mechanical advantage. We've calculated it to be 20 upon velocity ratio. We have 314.2, then multiplied by 100%. So that implies that our efficiency will be equal to efficiency is 6.36%. That is quite low. So this machine is not very efficient. It's not very efficient. As you can see, the velocity ratio is very high. So we expect the efficiency to be low. So it has very low efficiency.